Zoom in, I hear you. Today I see my student at 8, they are like super zombie. Why? Okay, so previously, when we looked at magnetic fields, we spent so last time, right, this chapter got 2 sections. It's 2 different chapters, right? But they combine it again, I guess, so that it looks like you have to study less. But actually, the learning outcome is all the same. The only thing that they remove is the magnetic resonant imaging, or MRI. But to me, it's about the same content. It's not that much, not that few. It's the same load. Okay, so for magnetic fields, the first part, we look at force. And how can you get force? Our first option is to have a current. So force is BIL. This is I, this is B, this is F. All right. Second option is to have moving charge, which kind of is current, right? Because current is a moving charge. So this one would be moving charge. And from here, you get F is equal to BQB. So you must have a charge moving at the speed V. So from here, we looked at different examples, like the current balance, the Hall effect, the circle, all that. But today, we're going to ask ourselves, what happens when I take magnetic field and see if I can create current? So current can create a force. But is there a way where I can create current? I can flip the switch and then use a force to create current? Yes, but the conditions are a little bit more complicated. Okay, so most of the time, right, when you think about induction, you would think about I don't know whether your school teacher got show you the demonstration. I mean, my school teacher got show me last time. They take the coil and they move it in and out of the magnet, and then you can see I guess, maybe if it's connected to the light bulb will shine. If it's connected to a galvanometer, the galvanometer will deflect. So since we don't have a lab, I guess I will try to load a simulation for you to look at. Okay, but what we are going to look at now is the product being current. So this one is the first part, force. And then if let's say I were you and I'm the type where I learn better if I reorganize my notes or reorganize my brain, I will actually, I think I've drawn this quite a few times before, branch out what are the different examples. Okay. So this creating current, there is actually a law, okay? And here is kind of called the law of electromagnetic induction. And I'm waiting for it to load. Are you okay? So while we wait, I probably need to introduce some other main ideas in this portion. Which is the laws of electromagnetic induction. We are still in chapter 20. Okay, so if you are following the syllabus, this one is chapter 20. Let's see. 20.5. Okay, so if it doesn't load, then the other recipe I got. Okay. So I don't know whether you've seen this before, but if let's say I have a coil, and this coil is a closed circuit that is connected to this one, maybe I should put a voltmeter here. Okay, and then I will show you the magnetic field lines. So currently, right, the field lines will pass through the coil, okay? And nothing is happening, it's like very boring. But if let's say I were to move the magnet in and out, I like how this one got a strange sound effect. I shall share the sound effect with you. Okay, so you can see that as long, so in Form 5 time, your teacher probably will tell you if the lines is cut. Yeah, got cut. See this cutting? But it's not just cutting, right? Cutting is not a very scientific term. It's not a very scientific term. It's just a way to say that there is certain changes happening inside the coil as I move the magnet. So when I move it towards, it's negative. When I move it away, it's positive. And then if I swap it, move it towards is positive, move it away is negative. Okay, so we're going to look at the laws that govern the magnitude of the voltage, meaning why is it when I move faster, the light is like brighter compared to when I move it slowly. Okay, and also what decides the direction. Okay, so before that, because we need some maths or we need a way to quantify these lines passing through a closed area. So we will call this magnetic flux, not to be confused with magnetic flux density. Okay, magnetic flux density is B, is to show you how strong the field is. Whereas magnetic flux, this symbol phi, is defined as, let's say you look at this surface area, there's a cross-sectional area here, right? It's like a coil. Okay, so it's defined as the product of the area and the magnetic flux density. So okay, I'm not going to shape the whole thing, but let's say this area, right? It cuts through. Let's say this is the line that is perpendicular. So this is the part that is 90 degrees to the area. So let's say this is a vector for A. Okay, if I look at the top side, right? You watch arcane. If I look at the top side, okay, what I will see is actually I have the coil like this. But then the magnetic field, let's say I represent magnetic field with blue color arrow, magnetic field is passing this way. Okay, so right now the angle that I have here is theta, right? So of course, if I want maximum penetration, I will have the magnetic field going in this way. Right? If I have zero penetration, then the magnetic field will go like this. Or rather, maybe I rotate the coil. Okay, keep the magnetic field like this, then the coil this way. So in the first case, this flux is defined as zero because there's no field line that passed through the coil. Yeah, this top part here is this one. Okay, all right. Here is maximum flux. And this maximum flux is the 90-degree one. Here is between lah, neither here nor there. So this means, right, it will be helpful if we actually resolve your B. So I'm going to resolve the B, one component that is parallel to the coil. This will be B cos theta. The other component that is 90 degree, B sine theta. Very long time never resolved already, right? Okay. So in this case, right, I will take the component that is 90 degree to the coil. So from here, I will define magnetic flux as the product of B and A. Magnetic flux density, because we need a number to tell us how much magnetic field passes through a unit area. So product of magnetic flux density and area normal or 90 degree to the line of flux. And actually, the actual mathematical term for flux, right? We can represent like this. This will be equal to, magnetic flux is phi, vector B dot vector A. Okay. We need to settle the issue of angle, right? So let me copy this and bring this down with us. Okay, regarding the issue of angle. So which angle to take? If let's say you do maths and you know the dot product or the scalar product, you will know that this is actually BA dot, right? So it's cos theta. But this theta has to be between this theta, this angle have to be between vector B and vector A. So actually this one cannot use theta because we use theta for something else already. So maybe this one we will use phi. Okay, cannot phi sudah pakai. Okay, like alpha. Cos alpha. Okay. But you see, most of the time instinctively you want to use theta. So it can also be flux is equal to BA sine theta. And this theta here, this is my theta. This is between magnetic field and the plane of the coil or the frame or whatever you want to call it. Actually, this one is the frame. Okay. Which one do we normally use? We normally use this. But for those of you who do maths, I want you to know that it's actually a scalar product, which means flux is a scalar. Okay. So this one need to know. We'll take the part that is 90 degrees. Oh, by the way, where is vector A? Vector A is 90 degrees to the plane of the coil. So if you want to, I will draw A here for you. This is vector A. So those of you who do maths, vector A is defined as the unit vector perpendicular to the surface area of a coil multiplied by the magnitude of the area. That's why you learn unit vectors. Or at least I hope you learn. Okay, but for physics, what you need to know is just the product B times A. B times A, but also remember to mention the direction, normal to the line of flux. So 1 mark each, normally is 2. Okay, so flux, right? The unit is Weber. WB. So this one is unit for flux. And 1 Weber can be defined as 1 because flux is BA, right? So the unit for B is Tesla. So the unit for A is meters. So it's Tesla meter squared or 1 Tn squared. Okay, lor. They ask one time only, don't know why they ask, but just give them units. If they ask you to define units, you use the defining equation to take the units. Okay. All right, that's it. And of course, sometimes we have more than one surface area, right? We don't just, have that one area. Sometimes we have many turns of coil. So in this case, right, when it's one turn, the term that we use is magnetic flux. What you learned just now, right? Because this happens to be 90 degrees, so flux is, normally we use lowercase lah. This is BA, okay? But if I have many turns, then every single coil, right, every circle is linked to the second coil. So let's say this is coil number 1, then this is coil number 2, then this is coil number 3. 1, 2, 3, 4, 5, they're all linked together. So this is N turns. So that means your magnetic flux linkage This is a term. Because we have many coils linked together, it's simply NBA, National Basketball Association, because one round is BA, N round, NBA. But of course, life is not always good. You don't always get 90 degrees. Right? So let's say I replicate the coil, but maybe I have my magnetic field go in at some weird angle. I like that. Okay, maybe I rub off a bit so it looks more like this. 3D drawing is the bane of my existence. Okay, so this is the plane of the coil. So maybe this one is my theta. So from here, your flux with small lowercase phi is BA sine theta. So I'll always take the angle between the field line and the plane of the coil. I don't have to care about the dot product or the scalar product right now because, you know, we don't use scalar and vector product in physics. We don't use the IJK method because physics is supposed to be able to be friendly for friends who don't do maths as well. Okay, well. So let's look at this one. Let's say now you have another magnetic field passing through this. Of course, in this case, your flux is NBA sine theta. Okay. Why is it that we start off with flux? Because we need to understand that this is a convenient way for us to calculate the magnitude of the current that we create. So for example, if I move the magnet faster, I see a brighter light. So it has something to do with rates, right? Because faster is the definition of rate. Faster I move, the brighter the light, the greater the current. So this brings us to Faraday's law of electromagnetic induction. So Faraday's law of electromagnetic induction, it says that the EMF induced. So I want to pause for a while and try to remind you what we mean in science when we talk about the term induce. So induce is like terpengaruh, because this in Malay is called arus arohan. Teacher, how you know? I learned physics in Malay in high school last time. So it's dipengaruh. I don't have current one, but this annoying magnet, okay, let me show you. I don't have current, you know, I'm just chilling here. I don't have a power supply. But this annoying magnet, now I got current, no. Terpengaruh. Okay, so that's why when we say induce, it's actually being affected by some changes in your environment. Bad influence, good influence, I don't know. Like something changed your environment and then something changed inside of you. Very normal, right? It's a very human thing, right? Something changed there, then something changed in your heart, it's normal, okay? So the EMF induced is, but this EMF will not induce in any random place, okay? You pick up a piece of metal, like my spoon here, and go like, oh, EMF induced. No. So EMF must be induced and they must be placed for the charges to move. So in a closed conducting, look at the coils on top, they're all closed conducting loops, is directly proportional. Directly proportional to the rate of change of magnetic flux linkage. So there are two main things here. Number one, we have EMF or electromotive force or battery that is induced inside a loop, inside a closed conducting loop. The second part here is directly proportional to the rate of change of magnetic flux linkage. In other words, right, if I write this whole sentence in the equation, I have induced EMF and I need a symbol for this. So I am going to use maybe epsilon or E also can. It's directly proportional to the flux dt, or you could also say induced EMF is directly proportional to d n flux, because n turn over CIE, right, is a little bit annoying where these two sign of flux is interchangeable. That's why when I teach also it feels like an interchange. Okay, so read the question. This is the flux dt. Okay, I'm just going to take the most cleanest minimalist version. Okay. So Faraday tells us the magnitude of EMF. But remember, when I move this magnet, E is plus and L is minus, the voltage deflection. This one will be Lenz's laws territory. So Lenz talks about the direction of the induced EMF. Which direction is the current flowing, right? Because obviously the galvanometer flipped from positive to negative, the direction of the current changes, okay? But this law is also quite intuitive because I like to call this the pembangkang opposition. You say go left, they will go right. You say go up, they'll go down, okay? So this tells me that the direction of induced EMF or current, depending on the question, causes effects to oppose the change producing it. The key word here is causes effects to oppose the change. Okay, so what are the examples of the effect? We will go through different types throughout the whole chapter, but these effects here could be force, either attraction or repulsion, depending on the situation, depending on the change. Okay, it can also be energy loss, because you want to oppose the change, right? Energy lost that is converted to current or electrical energy. But all this is to say that because the direction of EMF is negative, so I'm going to add a negative sign here. So this negative sign is to show opposition. And if it interests you, Faraday looks like this. This dude with the cigar and the strange looking bow tie. And Lenz looks like this guy. This uncle that looks a bit like the Pakcik KFC. Right? Just needs a beard and the uniform. Okay. So what have we learned so far? We have learned that there's this thing called magnetic flux. And magnetic flux is simply the product of the magnetic flux density, B, and the area that's 90 degrees to B. Simplified can be calculated using BA sine theta, where theta is the angle between magnetic field line and also the plane of the area. Second thing. The reason why we learn about flux is that current can be produced whenever there is a change in flux. I just need to change the flux. And the direction of that current will oppose the change that I make. So, for example, let's go back to this question. Let's say I change the flux by bringing the south pole closer. And when I do so, the coil is like, yo, south pole, chill, don't come so close. COVID-19 So this coil will become south pole and push it away, go away. Then current will flow in one direction. So just now, when I bring the south pole closer, it goes to the positive, right? And then if I pull the magnet away, it goes to the negative because the coil be like, I had a south pole. Why you go away? Come back. So the coil will become north pole to try to pull the magnet back in. But CIE, very weird one. The explanation have to be written in a very specific way. Okay, so today we're going to look at basically a very different types of case and then use it for electromagnetic induction. Use the laws. But this subtopic is finished already. It's true. Define magnetic flux as product of magnetic flux density and area. Recall and use. Understand and use linkage. So this part, when they say experiments, this is very ambiguous. So CIE have asked very, very different. There's not like, oh, let's just study this 5. So when you study magnetic field, more or less the examples are fixed. But in this chapter or this part, you can ask anything. Okay, so let's not panic first. Let's start with the easy one, or something that hopefully you can visualize. Not to scare you, but hopefully you can visualize. I'm going to start with using the diagram that I've used just now. This is the old paper, but I think it's a easy enough paper for us to start. So when you're asked to define B, I think we have defined it countless times in the previous parts, so I will leave it to you, okay? And generally, I will use the equation F is BIL sine theta. So B is equal to F over L if I is 1 ampere. And sine theta is 1, so theta is 90. So this definition is force per unit length. If you're referring to the notes, you will have to find chapter 23, page 27. Okay, so this one is force per unit length. Acting on a, think about the setup. I use BIL, right? So straight conductor. Remember the condition. What's the conductor doing? Carrying 1 ampere of current and then 90 degree normal to the magnetic field. So force per unit length is 1 mark. Straight conductor carrying 1 ampere of current is 1 mark. 90 degree to the field. Yay. Bonus. Don't leave this empty. So we've looked at this before, and you're asked to state Faraday's law of electromagnetic induction. So let's say E is proportional to the flux. Preferably, please write the whole sentence. So in this case, induced EMF is directly proportional to the rate of change of magnetic flux linkage. So last time, right, the physics question, a lot of it is definition, which is pretty nice. But I want to draw your attention to the graphs on the other side. Here. So it says here, using symbols A, B, and N, by making reference to the magnetic flux linkage in the coil, derive an expression. Okay, so this part is sort of straightforward because magnetic flux is equal to BA sine theta. So for a coil of N turns, flux will be equal to NBA sine theta. That's all. Very nice one. Then we look at the recent question after this. But let's see. Your magnetic field changes like that. So at first it is constant, then it go up, then it go down. All right. So let's think about the coil a bit. How did this magnetic field change? How did I, increase this magnetic field, decrease this magnetic field, and then bring it to 0? I vary B by changing the current in an electromagnet. Okay, so you imagine you have a large solenoid, and then the flux inside is like this, right? So you see this part here, it looks very uniform to me. Then here I can put my little frame here, like that. So what I need to do is I just need to change this current. If I change the current in the coil, I will change the magnetic flux. Make sense? So just want you to know that this is by changing the current. Okay. Put here. Yeah. All right, so we're going to change the current, and when we change the current, we will change the magnetic flux. And you are asked to draw the induced EMF in the coil. Okay, so let's start first by using the fact that your induced EMF E is proportional to the flux. But since this one is a coil, right? So E is proportional to d dt NBA sine theta. So the coil didn't rotate. Okay, I think they mentioned this one. The magnetic flux is made to vary in time t. So coil did not rotate. And what you have here is, let's say I put the equal sign. The constant is actually 1. So you can immediately sub it with an equal sign if you want to. And here, to induce EMF, take out all the constant. Number of turns in the coil is constant. Area of the coil is constant. And I didn't change the orientation of the coil. So sine theta is also constant. Throw everything out. And what you have is dB dt. So induced EMF is proportional to dB dt. dB dt, now B here, T here, dB dt is gradient. So induced EMF is proportional to gradient of your BT graph. Okay. All right, teacher, this one draw gradient function. Yes, that's why you learn how to gradient function in maths. At least I hope you learn. So let's check out this portion here. Here, dB dt is 0 because it's flat. So the current here will be 0. Okay. After that also 0, I draw the after that one. Okay. This part here, 0, 0. All right, let's look at this part. Now this part here, your magnetic field is increasing. It's going up. Okay. So you could say that this one is positive. And then you remember lens. Lens is like, I don't like that you increase. No. So because of lens, or thanks to lens, you get a negative sign, negative sign, negative sign, negative sign. Negative sign. This thing is 10 to our friend length. The whole thing is Faraday. The negative sign is length. They are both important. So if this is positive, it means that when you reach here, this part is going to be negative. Okay. I don't know what value this one is. Let's put a number lah, -3 volts. We'll calculate later, but currently we're just sketching the graph. Okay. Let's look at the second portion here. From 2t to 3t, it decreases. So your dB dt is negative. And what happens when things decrease? I panic and want to increase it back. So the direction of the current will flip. The direction of the induced EMF will flip. And because the change is faster, this is double. So if down there is 3, then up here you draw 6. Right? Okay, that's all. CIE is very nice one. They are not very particular. They are not very particular about the symbol. So as long as the blue color section is negative, the blue color section and this pink color section is not the same polarity, CIE is okay. But if you really want to draw it properly, your induced EMF is proportional to negative deflux dt. So this deflux dt, this or dB dt is positive. So from here, this is negative because EMF is equal to negative dB dt. And dB dt is positive. So you get negative value. And then here, your E is equal to negative dB dt. Because this dB dt here is negative. So negative, I'll get a positive value. Because of Lenz's law. Lenz's law introduced this negative sign. Okay. CIE, generally, they are not strict. So if you draw your graph like this, positive, negative, also okay. You won't lose marks. But the correct one is negative then positive lah. Because you want to oppose the change. Here, the flux increase. You want to fight the increase, so you make negative law. Then here, the flux, let me zoom out a bit. Here, the flux increase. You want to fight the increase, you make opposite direction. Then here, decrease. You panic. Why decrease one? Then you try to make back in the same positive direction. Or use maths. Also can. Right, let's practice a bit. We gotta practice. And we gotta refill my little water. Stay hydrated, guys. If you drink your water, your brain is, I think, 80% water. Okay. If not, can become potato. Okay, let's do some graph sketching. Okay, this is very similar. We're going to look at May, June 18, paper 4.2. But need to do a bit of calculation. Okay, May, June 18, paper 4.2 is page 21. Okay, to the person who is asking about the sine one, which is something to do with Lenz's law, you okay now? Practice. Let's see if we really can or cannot. Okay, this is in page 21. Do you need me to find the notes for you? Sorry, I didn't do that just now. In Google Drive, it will be in the topicals, but chapter 23. because the college student that I teach haven't reached here yet, although they are sitting for the same exam as you. Yeah, you know lah, 1.5 year program. Rush until no day, no night. No. Rush. So who je lah. Okay, this one is page 22. Okay, what is meant by magnetic flux linkage? Not B, hello. This one is magnetic flux density. So we talk about B. This one is magnetic flux linkage. This is phi, which is BA sine theta. So right now, product of magnetic flux B, magnetic flux density B, and cross-sectional area. They call it a coil already, so we can say of a coil A. Where, or we could say, where the magnetic flux density B is perpendicular or normal to the cross-sectional area. All right, moving on. Here you have a coil, 160 turns, diameter 2.4. And got D. Coil is situated in a uniform magnetic field of flux density 7.5 millitesla. Okay, got D. This one sort of look like this, right? I mean, rectangle, circle, all same. Now we know how to find the area. Okay, so the direction of the magnetic field is along the axis of the coil like this. Beautiful. So it's 90 degrees. Full penetration. Magnetic flux density is reduced to 0. Reduced to 0. So from 7.5 millitesla, I drop to 0. So B against T is like that. I mean, I assume it's uniform. They say average, so I assume it's uniform. So here is 7.5 millitesla, and this time here is 0.15 seconds. Show that the average current or average EMF, induced in the coil is 3.6 millivolt. Okay. So in this case, we already have all of this information. We can use Faraday's law, where the induced EMF is directly proportional, or in this case, equal to the flux dt. The proportionality constant is 1. We can just use this one direct. Okay, so I'm going to start with this one. E is equal to the flux dt, and eventually, I get d dt. What's the flux? NBA. I mean, if you want, you can put sine theta, but theta is 90 degrees. Okay. So whatever that is constant, I throw outside, okay? Number of turns is constant, 160. Area is, magnetic flux density is not constant, okay? B is changing, magnetic flux density is reduced to 0. So I leave B inside the differential, but I can take out the area, and then I can take out sine 90. Okay lah, then this one is dB dt. Okay. This means I need to find the area. So EMF is equal to 160. This looks like a circle to me. So it should be pi r square, or in this case, pi d square over 4i. I put pi r square now, 1.2 cm. Pi times 1.2 times 10 to the power -2 bracket square. Okay, so we can find the area. And this is dB dt. But wait a second. If we want to find average, right, I just need to take the change in B, divide by the time taken, change in time. So finally, right, my E is actually 160 N. And then this is A, 1.2 times 10 to the power -2 square. And this change in B over T is reduced to 0. So if reduced to 0 from 7.5 means I will take 7.5 minus 0. Teacher, the magnitude, I'm looking for magnitude, not direction. Okay, so you want to put 0 minus 7.5 also can, you want to put 7.5 minus 0 also can. I just want the magnitude. So I'm just going to use the big number minus the small number. Right, the time taken is 0. You know, we can press calculate. Square times 7.5 divided by 4. So this one is 3.61. I am missing. Oh, millitesla. This is millitesla, by the way. So it's 3.61 millivolt because the 7.5 is millitesla. But if you are generally a bit anxious about prefix, then I would recommend you just convert this one times 10 to the power of -2. Okay. Just give me some notes. Okay, I believe this calculation is true. So the important, I am doing it slowly and substituting it step by step. Is it really needed? No. Just show the key steps. Why not the key steps? To refer to my best friend. And my best friend, I mean the marks. Paper.sc is a great student. Having a bad day. Right, so if you mention something along the lines of EMF is the flux NBA sine theta over T, this part will give you 1 mark. And then the substitution here is your second mark. All the everything substitution. Okay. Okay. Next. So now this magnetic flux density that was previously 7.5, so you can see this one is 7.5, varied as time shown. So it was 7.5, 7.5, 7.5, 7.5, and then it dropped to 0 in just nice the time that we mentioned just now. So from here to here happens to be 0.15 seconds. Then here, 0.15 seconds. So this happens to be the same amount. And then it will stay 0 until it decreased another to negative 7.5. Actually, it's changed direction. So here, the magnetic field decreased to 0, stay at 0, and then from here to here, increase in the opposite direction. So from here to here, B increases to 0, and then from here to here, B increases in opposite direction, opposite to initial direction. That's why it's negative 7.5. And if you notice, this one is half. Half the time I increase So this is 0.75. 0.75 no, 0.075. Is it though? 0.1, 0.2. Actually, no. So it's 0.1. Yeah, 0.1. And then this is 0.075. Yep. Half mark. 15 boxes, 7.5 boxes. So you know what's next? We are going to sketch the EMF against time. So I'll give you a few minutes. Sketch induced EMF against time. I'll give you a hint. We already calculated this one. From the previous section, the induced EMF here, magnitude is equal to 3.6 millivolt. Magnitude of induced EMF. So try to use this information and also the shape of the graph to sketch this. All right, I'll give you 5 minutes. And I'll go and refill my water bottle. I am let's check the graph. Okay, so it's a graph, and I think the first thing I want to draw is when everything is zero. Zero is kind of like my favorite number. Okay, so from 0 to 0 0.1, the induced EMF is 0. Get the easy mark first, right? So from 0 to 0 0.1, EMF is 0. From 0.25 to 0 0.35, EMF is 0. 0.25, 25 is here. EMF is 0. And after 0.425 onwards, EMF is 0. So 0.425, 0. Okay, so try to make sure you draw until half a box in the exam. Use your rulers to help you. Okay, so here is going down. So this gradient is negative, right? Right, negative dV dt. Meaning this will become positive induced EMF. Of course, you go down and panic. I want to create back the current that was gone. You know, actually, I want to create back the magnetic flux that was gone. So I try to make back this one, meaning this one should be 3.6, right? Okay, now they are 3.6. 1, 2, 3, 4. Yeah, 3.6 is here. So 3.6 all the way. You join. Is it called 1.5? It's 3 boxes. Okay, so 2.6, 2.6, 3.6. There we go. You want to draw full line also can. I prefer drawing dotted line because the full line a bit straight. Okay. Then here to here is double. Double because it's half the time. So I'll make a note here. Here to here, half the time taken. So faster, right? And because it's faster, it is double the EMF. Faster ma. Rate of change, if the rate of change is greater, actually the rate of change is doubled because the time taken is halved, then the EMF is doubled. So instead of 3.6, we will have 7.2. Okay, so let's ask the chat. Do we think it is 7.2 in the positive side like this? So this is option number 1. Or 7.2 in the negative side. Which one did you draw? I'm curious. You draw the positive or the negative side? Let me know in the chat. Which one did you draw? Negative. Okay. What about the rest? The quiet ones. Positive, negative. Don't know also can say I'm not sure. If you want to, I'll show you back the graph. Try to think about gradient. Wi-Fi is quite unstable. I didn't catch what you said. Ayo. Okay, so what I said was, do you think, okay, here is 3.6, right? And it's positive 3.6 because the dB dt is negative. Okay, so negative dB dt is equal to positive EMF because EMF is equal to negative dB dt. So positive 3.64. So my question was, for this second portion, which is 7.2, because it will be half the time, so double the EMF. Do you think it's positive 7.2 or negative 7.2? Positive 7.2? Negative 7.2? Millivolt lah, but which one? Not sure. Okay. So let's ask ourselves, what is this gradient? Positive or negative? Or you could also just ask yourself, is this gradient the same sign as this gradient? Is it the same sign? They're both going down, right? Same sign. So this one is still negative dB dt. Can I? So if it is negative and you want to fight the decrease or actually increase in the opposite direction, your induced EMF E is negative dB dt. So if dB dt is already negative, means here we are going to put negative dB dt. Tell me what you get. Positive or negative? Positive, right? Okay. Negative, negative, they come together, become positive lah. So dB dt, and we actually calculated this already. We actually 3.6 or 7.2 calculated already one. So this one would be positive 7.2. Okay. So just for comparison, I'm going to scroll up to show you here. This one, the reason why you have flip sign is because the gradient is opposite sign. Go up, come down. So negative, positive. Negative, positive. Whereas for this one, the gradient is just down and more down. Okay, lor. Positive and more positive, lor. Then teacher, they give me much space here for what? To confuse you, lor. Were you confused? If you were, then they did their job. You okay? Hiya. Okay. Let's do another one. Gotta practice. Okay, this one is page. Page 29. Second. It's almost an identical question. So this subtopic can be quite challenging if you want to speed run. It's not a chapter to speed run. So we'll spend some time starting with you. So this is a setup. Macam sama kan? It's the same thing, but it's a slightly different picture lah. And then even nicer, they gave you the changes in magnetic field. So this, as you can probably tell, this shape can be anything. Today they draw like that. Tomorrow they draw like that. Staircase. Then after that, maybe they draw like this. Okay, well. But it will be a straight line. Okay. So first part, you are asked to show from 0 to 0.2. So here to here, that the EMF is 0.08 volt. So I'm going to temporarily crop this. Stuff it top here. Okay. So this is the magnetic field. It increased from 0 to 45 in 0.2 seconds. Right? And this is the setup of the coil. So I'll give you some time. Do you need the question? Or do you want to look at the working previously? Yeah, you let me know which one you want. I will leave the question here. What year is this from? Oh, sorry. This one is page 29. It's page 29. May, June 20, not too long ago. Paper 4.1, question 9. I go and find link to paper for you. Link to the hand. Try. Do now, because now is the prime sleepy time. So if you passively listen to me, pepper, you might actually fall asleep. You can wake yourself up and maybe try to do something. Okay, so this one should be able to bring you to the PDF document. And this is in page 29. Do part A. And if you can, then you can sketch the graph also. You know what graph I'll get you to sketch, right? Induced EMF against time. Right, I'll give you maybe another 5 minutes or 4 to 5 minutes. Try to find the EMF induced in the coil. I'll write here for you. The magnetic field increases, in case you got too many things to stare at, increases from 0 to 45 millitesla. 0 to 45 millitesla in 0.20 seconds. If I play rave music, can help you stay awake, I'm happy to. Okay, let's check your calculation. I'll skip some steps this time. Get a bit of space. Induced EMF E can be calculated using the flux dT. This one is just magnitude. Do I include the negative sign for Lenz's law? I can if you want to. I'll include it for you. It's okay to include it. Don't include it also, never mind, because we just want to find the magnitude of the EMF. So this will be negative d dt n dA sine theta. I always write this because I know this one got 1 mark. I want that 1 mark. I know if my answer all correct, I'll get marked, but then I want to have insurance plan. Okay, so I can take out all the constants now. N, A, I guess I can substitute immediately. All right, so N is constant, and we're talking about 350 turns of wire. A is pi r squared, so 3.6 times 10 to the power -2 square. Then sine theta is 90. So what you have left is change in B over change in T. But the magnetic field changes from 0 to 45. So I can just substitute this one with 45 times 10 to the power -3 divided by 0.20. Okay, that's good. So I'm pretty sure we plug all this into my friend Casio, the calculator. Should we get my 0.08? Oh no, wait, this is diameter. Need to change to radius. 3.6 divided by 1.8. Yep. So I got 0.080157. So 801, which is 0.0802, my bad. Is it just 0.080? Yeah. Okay. So this kind of questions, when they give you answer, is sort of like a bonus because you can check. And if let's say you did something like, oh, forgotten to convert diameter, or use the radius instead of the diameter, you should be able to figure out the error because the answer is given. The second reason why they gave us the answer is because it will allow you to plot the graph correctly. Even if you can't calculate this, you can still use this 0.08 to calculate the graph. That's partially why lah. Okay, so let's carry on. We're going to sketch a graph, my friends. Namely, the induced EMF against time. Let me close the graph. You see, they're very generous with graph one. It is 4 marks. It is so nice. Okay. I put the shape here last, small, you can compare. How would you draw this on here? Okay. So what have we calculated? We have calculated for the first 20 seconds, the induced 0.2 seconds. The induced EMF was 0.080. Is it a positive, negative? You decide. Okay. But let's look at this one. This part, the decrease is the same. You still went from 45 to 0, but you took double the time. So double the time, what's the EMF here? Can someone tell me in the chat? What do you think this EMF is? Double the time. I took a longer time to decrease from 45 to 0. What is the EMF for the second portion? Get the magnitude right first, then we decide the sign later. What do you think? Double the time. And we decrease the same amount. I guess you could repeat the calculation, and the only thing you will change is this 0.2 to 0.4. There, this calculation. This part here. Everything else is the same one. I didn't change anything about the coil, so this part is the same. I sort of have the same drop in magnetic field, so this 45 is still the same. This 0.2 is for this 0.2, and I got 0.08 volts. But right now, I double the time. So 0.2 becomes 0.4. There, here to here is 0.4. So help me out here. What is this? 0.04. Good call. It would be halved, right? Because it took a longer time. So 0.040. Next part. These two signs same or not same? What do you think? You think the sign is the same? The sign is not the same? Think about the nature of their changes. One is increase, and the other one decrease. So the nature is different. So this one must be, if this is positive, then the other one is negative, and vice versa. So I'm just going to make a note here that these two will have opposite sign. And they have opposite sign because here increase, here decrease. Okay. Can I use the gradient, teacher? And here is positive gradient. Positive gradient means negative EMF. Here is negative gradient. And negative gradient means positive EMF. Are they very strict about this? No. As long as you know that they are opposite sign, you're good already. But you want to be very accurate in case you do more magnets in university, then please know that it is a negative gradient function. So if you see positive gradient, you draw negative value. You see negative gradient, you draw positive value. So let's draw. Okay, 0 to 0.2, negative 0.08. Here, maybe 0.808, maybe 0.08 here. And then 0.4 to 0.6 is positive 0.04. So that would be 0.0234 here. Okay. This one, we can see that. Okay. Okay, what about 0.2 to 0.4? Can someone tell me what do you think that EMF is? At this missing section here. Okay. What is the EMF? 0, very good. Because the gradient is 0, can. Because there's no change in magnetic field, also can. So it depends on which one your brain likes. I will offer 2 ways to look at it. This stacking stuff. So this opposite sign could also be because from 0, let me just see both the graph and me right. These two will be opposite sign because from 0 to 0.2 second, B increases. The nature of the change is opposite. From 0.4 to 0.8, B decreases. So because the nature of the change is different, if one is positive, the other will be negative. CIE really don't care. I'll show you the mark scheme later. I'll show you now. I'll open up. Okay. This is one way to look at it. If you are the explaining type, okay, the nature of the change is different. So with increase, my current flow clockwise or left to right. Then decrease, my current will flow anti-clockwise or right to left. It will flip. Okay. So that's one way to look at it. The other way to look at it is like use maths as a convenience way, I guess, because maths will just say Yo, bro, remember how we found this negative 0.08? We did this, but this one here. Okay, my negative also went for a walk. Like, I need to introduce. Put it back, put it back, I put it back. Negative, negative. Okay. All right, that's negative lah. So I introduce it back. And right now, it's all about the gradient. E is negative gradient of the flux dt. But since flux is NBA, and this N and A, and I guess sine theta are all constant. Right? Everything is constant, right? So now flux is proportional to B. Can? Which means for this case, I can say that the induced EMF is actually negative dB dt. Of course, there's a constant here in front. All of these is the constant. This one, this one, this one. Right? So yeah. So we're looking at gradient. This gradient is positive. I draw negative sign. Gradient negative. I draw positive sign. Okay, done. All right. Teacher, can I just use one? For drawing graph, we don't really care how you get the graph as long as you can confidently sketch the graph. Okay. But later on, maybe today, I think we have time, we will talk about the second skill where you actually need to explain. So explain, you cannot just simply use any term that you like. Negative gradient, explain, don't have graph. Okay. So I will provide some graphs for you to try at home. But let me show you the marks ones. Because if you see graph, it's a very nice bonus, because the explain one is a headache for most students. So you kind of like, 5 mark, 4 mark, explain, GG lor. Okay, let me open the marks first, round out this question. Question. So this one, just both in opposite polarity. Okay. Marks here. This BD marks. So as long as you draw a straight horizontal line, it can be positive 0.08, negative 0.08. Like I said, they don't really care. Okay, you have a 0 from 0.2 to 0.4, that'll be the second mark. Third mark is when 0.4 to 0.8, you draw 0.04 or negative 0.04. Again, they don't care. So the final mark, 1, 1, 1, 1. The final one is when they're opposite polarity. This is the only time they care. And they just want it to be opposite. You can draw positive, negative. You can draw negative, positive. It's up to you. I think they are not that strict. The correct one, this is the correct one. But the other one was also accepted. Okay. Yeah, you like as long as you know it's opposite, can already. Square it out in your brain. Okay. All right. So these are two important skills that we have. Number one, can we use Faraday's law to calculate how much the EMF is? And because we stay away from calculus a lot in physics, although it's a very important thing, we kind of like run around it by avoiding it. So walaupun the definition got dB dt or d something dt, we just say, okay, average, then we just take the change divided by that. Or the change is always straight line. Okay, because we don't want you to not be able to answer the question because you can't do the differentiation. Okay. All right, second part, we draw the graph. Okay, so the second skill after calculation is drawing graph. Can you like based on this graph, draw this graph? Most of the time is they give you B, they draw E lah. But I'm pretty sure the reverse can happen. So I'll put a list of questions that you can try here. Okay, right? But I'm gonna move on a bit to talk about the explain part. All right. So before we move on to the explain part, I am just going to hazard a guess because I don't really know you because you never give me any work, so I don't know. But if you are the type that maths kind of makes you feel, okay lah, I understand. Like for example, I can tell from this equation, well, this everything here you find is constant, you know, if I double the time, etc., etc. This maths makes sense to you. The graph would naturally, as an extension, sort of begin to make sense. But the whole overarching idea, if I zoom out, is changes. Changes in flux causes EMF. No change, no EMF. Oh, then no change, constant, then no EMF. Okay. So the main idea, if we zoom out a bit from the skill set, number one, when we want to explain, we have to clear your brain. It's like tulis karangan, you know. If your brain is filled with other stuff, and then you have to write a karangan about, I don't know, banjir or something like that, you have to clear your brain first. Okay. So we're going to clear our brain and go back to what the laws are. So when it comes to explaining, number one, there is always, the story always starts with change in magnetic flux. Changes in magnetic flux. So remember, flux was NBA sine theta. Okay, of course, like all karangan, we have to write who changed the flux, right? If you say, oh, this person or this company caused the banjir, you must write lah who. So what causes the change in flux? Because we are going to have to explain that EMF is equal to d flux dt. So this d flux dt is already changed in magnetic flux. So we look at the equation. The good thing about physics is that there's an equation. An equation will help you remember how to change the flux. How? That's the first point that you have to write. What changes the flux? So there are a few possibilities. Number one, you could change the, okay, look at the equation. Or you think about the example we did just now. What have we been changing all this time? Teacher, you change B, you change B 3 times now. Okay, we change B. So change B. Magnetic flux density. How? Normally, we do it by changing current in a coil or a solenoid. Sometimes they don't really specify, but there was one particular past year where they specified. So you should just know there's a coil that I changed the current, and because I changed the current in the coil, I changed magnetic flux. Because remember, magnetic flux is directly proportional to current in the electromagnet. So sometimes some question can be very confusing because you have two coils. You can have, find the picture. Like that. Ini macam cerita dia. Like, sure, why got two coils? Why they do this to us? That's your understanding. Okay, let's look at the coil. You got one coil, small coil, and then you got this coil. Which is the coil with current? No need to induce one. I already got my current, no need to induce all. So which one already have current? The bottom one, because got battery now. Okay, like you close the switch. There's current flowing. Use the right hand grip rule. This side here is north coming out, south coming in. So magnetic field is this way, right? There are many ways to change the magnetic field, the magnetic flux density. The easiest way is to just change this current I. So when I say electromagnet, this is an electromagnet. This is not an electromagnet. You know why? Because there's no there's no power supply. Too thick. No power supply. So this means this one inside this coil, is the induced EMF. The main character that we're talking about. Here. This one. This coil is the one that will experience the change in flux. Because why? It happens to be beside an electromagnet. You change the electromagnet, and because I'm beside the electromagnet, I'm forced to change with it. And because of that, I oppose that change. So we can change the current in a neighboring coil. Adjacent neighbor. Let me get that. Okay, so this is an example. All right. Then you're like, teacher, what's so susah? Can I not just bring the small coil and put it far away and bring it closer and put it far away and bring it closer? Like what you did for the magnet bar. Can. You can change the distance. Of course you can. But a bit harder to measure lah. Easier to measure this current ma. I just put an ammeter here to measure already. To measure the distance. Okay. The second option is to change the separation or the distance, the relative distance between these two coils, here to here, x. So you can, by moving coils closer or further apart. So what am I not using? Cut the flux. Of course, I know if you visualize the purple color curvy line, and then you move close to the coil, and then you move away from the coil, this line macam kena potong lah. But as someone who learned calculus, this thing is very strange. Okay, so what it's experiencing is just change in flux, because if I bring it closer, here the field is stronger. If I bring it further, here the field is weaker. So change, move the coils closer and further. This one is pretty popular, as you can tell from the 3 questions that we tried. This one, not so much. Because why? Distance is complicated. Right. Okay. What else can we change? We go back to the equation. We have done B. Can we change the area too? Okay. We can change the area. We can change the area. And the easiest way to change the area A is to have a region of magnetic fields. Models. Yeah, to make my life easy, I'm going to assume all the magnetic field is just pointing into the paper. Then I have a coil like this. Black. Okay, I'm going to do this thing where I put the coil at different position. Okay. So first, the coil is here. This coil got no flux. No flux, no flux, no flux, no flux. Wow, flux increase. Do you see what causes the increase in flux? The area of the coil that is inside the field. Don't worry, they want you to calculate. You can see a calculus question here, right? I can see the calculus question there. This one moving with a velocity v, and then you need to do some chain rule thing. We leave that to maths. You just need to know the concept and write it out. So when the coil moves, let's say from the left to the right, as it enters the region of magnetic field, the magnetic flux will increase till maximum, right? And then it will stay the same until it exits decrease, 0. Interesting. So this means if I draw a graph of flux like that, against distance from any point now, let's say point A. So here is A. And any point now, let's say here is B. So only when the coil is here onwards that the flux will increase. So only here onwards, 0, 0, 0, 0. Once it enters, it will begin to increase to a maximum. So it will increase to maximum when this coil is here. Okay. So we're gonna sort of like increase to a maximum. And then it stays the same until it exits. Let's see, like that, no flux. So until here. Oops. And then after that, it will decrease until here, point. Teacher, is this a straight line? No, because the change in area is the fastest when you are inside, when you're at the thickest part of the circle. So if I draw the right shape, right? If I order to draw the right shape, it's going to look like this. So the gradient is increasing and then decreasing. But again, this one not that important. Okay, what is important is you can explain the change in flux and the current flow. Okay, so here is how we can change area. This is an example. All right, so we've done B, done A, we're not done N yet. This one is a bit controversial because it's not in your syllabus, but it's kind of in, I don't know, last time they used to say, oh, study transformer, so that I can tell you, oh yes, it is indeed in your syllabus because they specify. But if they just say any experiment, then let's assume it's still there, okay, in case they ask. We can change the number of turns or number of turns. So think of solenoid, EG transformer. And your transformer sort of like have like this, you know. And then this one, see before during Zaman SPM, right? Put the alternating current here. Okay. So what is going on is this flux keep changing direction. Maybe first it will be in this direction. And then in the next moment in time, it will change to this direction. And then in the next moment in time, it will change to this direction. So the flux keep changing direction. And what I'll do is, if I have a secondary coil here, then GG, the secondary coil actually changes the number of turns. So I change N, this is NS, and this is NP. Remember, here is your output. This one is your input. Step up transformer, this one. Okay, and finally, NBA, sine theta. So we can change theta. Change theta by rotation. Teacher, who rotate doesn't matter. Magnet can rotate, coil can rotate, as long as someone rotates. EG, also learned before in SPM, is called a dynamo. Remember the one with the slip ring or generator? SPM, you learn two, AC, DC, then you memorize to write SA one. This one, no need. But I will show you now some examples. So since we are at this question, I'm going to do part and show you what it looks like. There's a general template that I offer to students to more or less like help them visualize their essays. But I'll show you how I use the template here. Okay. So in this scenario, you have a bar magnet held a small distance above the surface of the aluminium disc. So if it's held a small distance above the surface, that means there is no friction. No friction between the magnet and the aluminum disc. Okay? So the aluminum disc is supported horizontally and held stationary. Magnet is rotated about the axis at constant speed. See, relative, there's rotation, because the disc is fixed and not rotating. Using laws of electromagnetic induction, which is your Faraday and Lenz, explain why there is a torque acting on the aluminum disc. Sure. Why? What torque? How torque? Torque is force times distance. Okay. So let me offer you a template. Number 1. And by the way, this is 4 marks. This is 4 marks. This is 4 marks. Not all 4 marks are equal. To be honest, I think this is an easier 4 mark. I'll just draw 3 lines at the right place. Then you get 4 marks. This one need to explain. Okay, never mind. So first thing, we're going to talk about number 1, is there a change in flux? So identify the cause of change in magnetic flux. What causes the change in flux? Teacher, duh, it's the rotating magnet. Okay. Second one, identify where is experiencing, okay, English a bit cha-cha, but where is there a change in flux? Where is change in flux? So as the magnet rotates, there is a change in flux in the aluminum disc. It'll be very obvious one, because there's only 2 things here. For the magnet, you got an aluminum disc. Why should I care about aluminum disc? Because I want to know why is there a torque acting on the aluminum disc. Okay, so that's the first part. I would say as the magnet rotates, the aluminum disc experience a change in magnetic flux. Whenever there is a change in magnetic flux, it's like level unlocked. Now I got induced EMF. So we move on to point number 3. If there is a change in magnetic flux, hence there is induced EMF. Where? At the same place. So please be very like super obvious where the induced EMF is. So then you can say hence the EMF is induced in the aluminum disc. Okay, you got 2 marks. Moving on. Now I need to think of this part here, like torque acting on the aluminum disc, can be anything in a question. Meaning the outcome can be very different. For example, like like this one. Some I record already. Like this one, they'll ask you, explain why the aluminium ring jump. Wow, got torque, got jumping. What else after that? Got some more. You wait, you chill first. The recent one that is not here that I'll discuss with you. Okay, here got another one. Got magnet, plastic tube, magnet, aluminium tube. Explain what? Explain why magnet B take longer time to fall through tube. Hiya. So you can see, right? This one can be anything. Don't know. Okay, but it is to guide you to the 4th or 5th, depending on the question, to the final point. I'm just going to call this point 5. That hence, let's talk. But how do we get there? How do we get to torque? In order to have torque, we need force. Okay, so now it's time to bring in Lenz. So when there's induced EMF, we move on to number 4. from Lenz's law, okay, the induced EMF sets up a current to oppose the changes causing it. Just going to fight the change. So if there's induced EMF, there is current. And because of this, current in the disk make friends with the magnetic field of the magnet. And this gives you your force. So I think the hardest steps, because you need to explain why is there a force. And when you have a force, then you can have a torque law. You don't even need to explain the last one. Okay, so let's write down the purple part. Magnet rotates, this experiences a change in magnetic flux. Hence, EMF is induced in the aluminum disc. Okay, then the next part will be, because got EMF, got current, right? Current flows in aluminum disc due to the EMF. This current interacts with the magnetic field of the magnet bar magnet of the magnet, causing a force on the disc. Causing force. And then this last part got no mark one, but you can round off your explanation and say hence, because there's a force, there's a torque on the disc. This one is actually a braking system. So in your car, right, we use Pascal principle, the hydraulic brake, to brake your car. You know, you press the piston and then the pressure transmits through the fluid, then brake your car. It's fine if you drive a car, perfectly fine. But what if you drive a train? How am I going to build a hydraulic brake from the first KTM car to the last KTM car? GG lor. This train driver must have the most strong legs ever. Just cannot lah, okay, not gonna happen. So there's an emergency brake where he pulls and then certain hinges will fall in place and it'll be friction, but then you probably need to repair the whole train after that. But there's a normal brake that they normally use, which is this electromagnetic braking. So the electromagnetic braking is as simple as I either rotate a magnet, or I even better, this magnet is always rotating, because why? It's a wheel, right? So the wheel is always rotating. But I just need to replace this with a coil. Ding, 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 ding. So if I replace this with a coil, the coil is like a magnet. So I guess if I turn on the switch and then there is current in the coil, it creates a torque. And if I make sure the direction is right, the torque can brake the brake. Like it's like applying brake on the system. Okay. So let's revisit our template a bit before we sort of end for the day. The template is like this. Number one, change in flux, where? Number two, induce EMF from Faraday's law. But please make sure you also explain Because some students will say there's induced EMF in the magnet bar, and I go like, that is not the right place, boy. It's not the magnet bar, it's the disk. Okay. Number 3, current flow. EMF current flow law. Again, where? Okay. Now here is where things become like anything can happen. That's why people say very hard, because the question always shows you the various outcome and you don't see yourself there. But actually, even if you totally have no idea how to get there, you write these 3, you at least get 2 to 3 marks out of 5 or 4, which is pretty good for a question that you don't know anything. It's half the marks. Okay. Then we move on, okay, and ask ourselves, when there is current, based on Lenz's law, it produces effects that oppose change. Effects that oppose change. This one is a bit philosophical, a bit strange, right? What are the effects? Okay, in this case, the effect is a torque to slow down it's like a braking force, okay? But anyway, or to make the disc start moving. So when the disc moves, the relative motion will change. But anyway, effects that oppose the change. The first one is that if there is current, let me change this current I. So this current I in a magnetic field will cause an opposing force. And this opposing force will create different things, will slow down a magnet, will cause the aluminum ring to jump. Okay, on the object experiencing the change in flux. In this case, it's the aluminum disc. On the object experiencing change in, why do this to me? Change in flux. Okay, that's the first part. It's there, change in flux, where? Okay. Second one that I haven't had a chance to discuss today, so probably cover it next week. Okay, we'll spend 2 weeks here, just trying out different scenarios. Second one, if there is current, there is electrical energy, right? Someone. So if there's an electrical energy, some other party, don't know who lah, or some other object is losing energy. Because this energy will be converted to electrical energy, which will then be dissipated as heat. Because things get hot. So you need to read the question carefully. Sometimes you can use both to explain an outcome. Because if you say something is losing energy and you say opposing force, it feels like friction, kan? Friction causes something to lose energy and it dissipates at heat. Yes, it also feels like friction. So depending on the question, the red color is possible, the blue color is possible, sometimes both is okay. So we will deep dive into this method because I think this one needs a bit of practicing. And jangan sekali they ask 2 types of explanation, which happens before, and a total of 8 marks is a bit, oof, we can't answer. Okay, so we'll focus on this. But today we not just looked at explanation, we looked at if there is what are the possible things that can cause a change in flux, which I've been through, because it allows you to start the ball rolling for this template. How do you know there's a change in flux? Then look at the question, something causes a change in flux, identify it, and then you can start the story. Hopefully it's quite obvious. Something is moving, something is rotating, something is turning on and off, something is, I don't know, moving closer and further apart. Read the question. Okay. So once we know how to find the change in flux, this is also from the fact that we can also calculate by using rate of change in flux how much EMF is induced in the disk or in whichever object that we're talking about. And once we can find the induced EMF, and if we have enough information about how the magnetic field changes or the magnetic flux changes, let's sketch the graph. Okay, so this topic, right, is about these 2 this Faraday and Lenz. The important thing that you have to learn, or hopefully you can master, is not so much as, oh, I'll study a fixed set of examples, because I'm gonna, you just do past years, some examples will change a lot, okay? So what we're going to do is we're actually going to look at how to apply the laws on 3 dimensions. Can you calculate? Can you explain? And can you graph? Which one do they ask? Your luck law, how I know which one will come out. If I know which one will come out, I'll be a very rich person. Millions of, I don't know, hundreds of thousands of people sit for Cambridge. Okay, so this is what you need to do. So I'm going to throw this into the usual Google Drive, all right? And I'll try to upload the videos a bit earlier, because I really think this one you should practice a bit more before we meet again next week. Not yet, next week. Okay. As usual, the suggested topical questions to try, I will dump it back here. I'll try to highlight some interesting ones, but try as many as you can. We will also work on the recent ones from ON21. ON21. ON21 is very interesting, but the recent ones have always been very interesting for induction. And it's also always been a difficult question. So we'll probably spend some time. Cool. Are you okay? Do you have any questions for me? Okay, ma. Okay, ma. Okay, that's all. Sorry for the technical difficulties. Good night. Thanks for staying out with me. I shall go and eat my dinner now. Bye-bye. I'm gonna stop recording.